and we can see that this bit's almost 20 years old, so Git's coming up on about 20 years here really soon. This is probably an apt description of Git because Git doesn't have a very good reputation when it comes to UX. It can be a fairly obtuse tool at times to use, but at the end, it's a very powerful tool, and it can really help and aid in developer workflows. So kind of with history aside, let's go ahead and kind of just jump into what a Git repository looks like. And so we're going to go ahead and make sure, can everyone kind of read everything on screen all right? Okay, cool. So what we're going to do is we're going to go ahead and create a new repository here. So I'm going to create a new repository. I'm just going to call it my repo. If you're following along, you can call it whatever you would like. And I'm going to go ahead and jump into this repository here. So now that I've created a new empty repository, it's completely empty. I'm not fooling you. We can see that there's no commits here or anything. We can see that our working tree is completely empty. We're not tracking any files or anything as expected. But if we take a look, we can see that there is actually, when we initialize a repository, we did create a .git directory. If you're familiar with Git and been using it for a little while, you've probably noticed that there's this .git directory. Well, what is this directory? Well, this directory contains the state of basically your Git repository. So all of your history, everything outside of this .git directory, we refer to as the working tree. And so that's kind of what you have checked out in your repository. You know, all of your source code or whatever it is, that's all checked out. But the actual state of what is all the versions and everything, that's stored inside of this .git directory in here. So what we're going to do is we're going to go ahead and take a look and see what it looks like. So if you're following along, depending on the version of Git you have, there may be some small differences between, but for all intents and purposes, all the main files, the important bits are going to be the same, and we're going to be talking about. So the first thing we are going to talk about is the head file. And some of you may be familiar with head, but what head is essentially, it is basically what your repository's currently checked out branch or reference is. And so that's what's kind of currently active. Being that this is a brand new repository, we don't have any references yet. But when we create a repository, there is a default reference that gets created. In this case, on my repository here, that's master. And so what we can do is we can actually take a look inside our head file. If we cat that out, we'll see that indeed currently our head file in plain text, it says that it's going to refs/head/master. Cool. Yes.
So is that a GitLab? I know that GitHub uses main now, or so master, is that a GitLab?
No, actually, it's Git itself just is always historically defaulted to just master. And then GitHub went and made a change. Whenever you initialize a repository through GitHub directly, you create a project and you initialize it, they'll set the default to main. I think GitLab has also made that change too. And the Git project itself is actually they're exploring changing the default to main as well.
You can set it up in your local configuration.
Correct, exactly. There is a configuration value that you can set. I mean, you can, the name of the default branch is actually relatively irrelevant. It could be foobar. It could be whatever you want it to be. Yeah, it's just a name at the end of the day. And it's just generally used to define what is the kind of default centralized branch for everything that you can go to. Cool. So we saw here, we can cat it out, see the contents. Another way you can access whatever the value is of the head reference is Git actually has a command for this. It is git symbolic ref, let me type in head. And we can see here that we printed out that the branch here is master. Actually, something I meant to touch on real quick, actually, I'll take a step back, is did anyone here actually know how many Git commands there are? Anyone, any guesses?
12.
12, okay. No, there's actually quite a lot. In fact, there's over 150 Git commands. Most of those you'll never touch, and that's perfectly normal and expected. I think most of us probably know like 10, and that's perfectly fine. But if you're ever curious, we can actually go git-help-a all, and that'll print out all of the Git commands that we see. And in this first section here, where it says main porcelain commands, these are probably the commands you're most familiar with. Porcelain commands meaning these are kind of the user-facing commands that generally users will use. So some of these would go down and pick some at random. You probably used add, branch, checkout, clone, commit, diff, fetch, init, log. Probably some of those you've used somewhat regularly or daily even. These are the user-facing commands that we use. But if we scroll down a bit, we can see that there are actually quite a few other ones, like these low-level commands here. And these low-level commands are all referred to as Git's plumbing commands. So you have your porcelain commands, which are user-facing, and then you have your plumbing commands, which are kind of the internal commands. These are used for things like scripting, but also used as building blocks by some of the porcelain commands. So some of the porcelain Git commands actually will fork and exec some of these internal plumbing commands. And later on in this presentation, we'll actually take a look at some of these plumbing commands and use them to inspect more closely the repository itself. Okay, cool. So back to going through, oh, yes, question.
Sorry, in that list, I noticed that one thing said interrogators. What is an interrogator?
So an interrogator is more of just being able to, I'm trying to butcher this, is just being able to get information out of the repository itself. It's kind of interrogating the state of the repository. So I think some of those, see what some of the, should spell it right. Let's see where I'm looking at it. Yeah, so like blame, help, let's see, I think if under it's there, show branch. So I think it basically kind of interrogates the history. All right. So where we left off. So we took a look at head. Cool. As just kind of another kind of quick aside, if you happen to have some fancy kind of terminal prompt that whenever you're in a Git repository and it shows the current branch you have checked out master, like I do here, that generally works by your prompt executing some script that goes into the .git directory and looks at whatever the contents of that head file is, and is able to use that to display that conveniently to the user in the prompt. Okay. So the next file we're going to take a look at is config. So this is exactly probably what you expect it to be. This is local repository configuration, and these are all just kind of the defaults that when you initialize a repository it has. We're not going to go into what these are, but this is kind of useful to take a look at. If you ever need to set some specific repository configuration, you can interact with the config either by directly editing this file, or you can use the git config command itself. For example, if we want to just list what the local contents of the repository is, we can do --list --local, and it'll print out all the local contents of our config in a slightly different format. Something else to note is that if you've been using Git on your machine, you generally also have a global config, usually stored in the user's home directory somewhere, and that will contain some global values. Usually you've set at some point when you set your machine, like your user name, your user email, things like that are used when you're writing a commit to put that metadata in the commit itself. Cool. Let's follow up. So next thing we're going to look at is just the description here. This isn't really something of importance to note, but because it's generally not used. But if you wanted to, you could put a description of your repository in here. It doesn't really matter. The next directory here is the hooks directory, and this provides the Git hooks. So Git hooks, if you're not familiar with that, is a mechanism within Git to execute custom logic scripts executables, essentially to perform various operations during Git. A very common example of this is if you've ever installed pre-commit or pre-push hooks in your repository. So like right before you commit or right before you push, you'll see that, or right after you type in those in, before the actual operation happens, Git will like spawn the script, and it might do something like validate your repository for something, or validate some code changes, or perform some sort of linting, or execute tests, whatever. It can be anything. But these hooks can execute that, and you can make it so even if it fails for something, so say it fails linting, it won't allow you to make the commit, or it won't allow you to push to the remote. There's a whole host of different types of hooks. They can do a whole bunch of things, and all the files you see here listed in the directory are just, they're not actually active by default. They're just templates that basically demonstrate some of the functionality that can be used by these Git hooks themselves. All right. The next directory here is info. This just contains some information about the repository itself. Nothing we're going to dive into too much here. The one file that it comes here with by default is the exclude file. You can think of this kind of like a git ignore file. It basically allows you to insert patterns into here, and then certain git porcelain operations will basically ignore those files. And then last two directories here, which are really the most important that we're going to spend the most time talking about, are the objects directory and the references directory. So first we'll note that both of them are pretty much empty. They don't actually have any files in there. They have some other directories in them. But looking at the references directory, so what exactly is a reference in Git? So probably you all are familiar with branches, right? And a branch is a form of reference. And basically, simply put, a reference is a pointer to some Git object. Generally speaking, it's a commit, but it could technically be any object within Git itself. Tags are another example of a reference in Git. So those kind of comprise as references. And right now, we have no references in our repository, so it's empty. Objects, on the other hand, are kind of the foundational building block of how we persist state within the repository for the actual contents of the repository. So there are 4 types of objects in Git. Does anyone know what they are? All right. So the 4 types of objects, 2 of them are probably well known. Commits, right? That's an object in Git. Another one are annotated tags. So that's the one that's relatively well known. Similar to tags, a little bit lightweight tags, a little bit different. And we won't go into tags too much in this. But the 2 really important ones that are less well known are blobs and trees. And the way you can think of blobs and trees, and actually I'll pull up this thing. All right, there we go. The way you can think of blobs and trees is that they are kind of analogous to a file system. So you can think of blobs like they're a file, right? So in your repository, whenever you add a file, there's always an accompanying blob with it. And that blob just holds the contents of the file in the repository itself, right? And so, if you create a new repository, has, let's say, just added a README or something, you commit that, there will be a blob containing the contents of that README file or whatever, your source files, you name it. Trees, on the other hand, are more analogous to, you can think, directories, right? So a directory will contain tree entries. And those tree entries will contain, maybe they'll point to 1 or more blobs. Maybe they'll point to 1 or more trees themselves. And maybe that subtree it points to will point to a blob. And kind of here in the example we can see here, we have a root tree. So at the very top, you'll always have kind of the root of the repository, which is 1 tree. And that root tree will point to any number of things. In this case, in this example, it's pointing to 2 blobs and a subtree that's pointing to another blob. So you can very much think of this as just Git's way of representing the state of a repository at a current point in time. Cool. Now, commits, on the other hand, commits are more of kind of like your snapshot. When you create a commit, it contains information, various metadata, like it'll contain like who made the commit, like the author, their email, the commit message, stuff like that. But it'll also include a reference to the root tree itself. And so that allows a commit to kind of encapsulate everything. So you can think of blobs and trees is kind of your building blocks of the actual contents and structure of the repository, and the commit kind of symbolizing a snapshot of that. So that's been kind of all fun and good to discuss, but let's go ahead and just show some examples of these objects themselves. It might be easier to see visually. So what I'm going to do is I'm going to go ahead and add a file to our repository. I'm just going to go ahead and just echo foo into a file I'm going to call foo. And we cap that. You can see we have a file named foo with the contents foo. So something kind of simple. You can see that it's currently unstaged. We'll add that and see that it's now staged. And we'll go ahead and commit this file as well to our repository. I'm just going to call the commit init to keep it simple. And now we've added that commit and run git log. We can see we now have a single commit in our repository. Cool. So let's now see. Also, just for keep things kind of clean, I'm going to go ahead and remove some of the not needed stuff out of our .git directory, just to keep things more concise. But now, if we tree our .git directory, let's see what's changed. So right at the top, we see that we have this new file here, git edit message. If we cat the contents of that guy, we can see it just contains the commit message we use. It's just a placeholder for the commit message we typed out. When we commit, it reads that and writes it into the message itself. The next thing we see here that's new is this index file. We're not going to go a ton into index here, but essentially the index is a representation of your working tree. Now that we've added a file that exists outside of the .git directory, we have a file in our working tree. And we can modify that file. We can make changes. We can add other files to it as well. And Git needs a way to track that. So whenever we make a commit, Git essentially will take a snapshot of whatever the state of the working tree is. And the index is able to keep track of what's staged, what's not staged, so that when you go and take that commit, that it's able to appropriately write the tree and everything. So if we have some time where we get some questions, we can maybe go into that a bit more in depth later. We'll leave it at that for now. The next directory we see here is we now see a directory called logs. And we'll come back to this a little bit more later, but essentially this logs directory is what basically keeps track of the history of references themselves. So whenever you're modifying a reference, you're updating something, you're adding more commits, your references themselves also update. Your branch has to update to point to the newest correct commit. And that all is tracked within these logs here. And we'll kind of come back to it. This is actually a very, very powerful feature of Git and really can get you out of a lot of trouble if you've ever messed up something. So we're going to circle back to that. Now coming back and taking a look at our objects and refs directory. Now we can see that there's actually stuff in it. Hooray. Looking at the refs directory, we can see that we now actually do have indeed our master branch that exists. And if we take a look at it, we can cat the contents of it, refs, edit, master. And we can see that when we print it out, we see that we have some string of text in it. And if we look really closely at that string of text, we can actually see that it matches kind of the third entry we have here, 9E57D8. Now, if you're following along, this you will probably have a very different string of text here than what I have here, and that's fine, that's expected. If you followed along exactly with what I have, the other two, though, should exactly match. And we'll kind of cover why that is later. But we can see that we do indeed have now a master branch that's stored in our refs directory, and it points right now to a file here, 9E5, etc. So we can probably, since we know our reference is pointing to a commit, we can probably assume that that file is our commit. Earlier, we added a file, right? We wrote a commit. We know since we added a file, we know that there must be a root tree that contains that blob. So we can deduct that we have here one tree, one blob, and one commit here. And that makes sense. Those are the three objects we see. So let's take a look at what they look like. So we'll just start by picking one of them at random, and let's just cat it and see what we get. And we catted one, and we get a bunch of gibberish. All right, so there's probably some binary data in there. Just as a sanity check, let's go ahead and check it out. Let's do this one. Also some gibberish. So what's going on here? Well, maybe you might guess that basically Git has compressed these objects to save space. So that's just an optimization, reduce the amount of disk space is taken. So if we actually really want to see what the contents of these objects are, we need to decompress them. And for that, I'm going to be using a tool called PIGZ. So if you have that, you can follow along. If not, no worries. And what I'm going to do is we're going to do PIGZ-D to decompress. And we're going to start with decompressing this one. So we just decompress this, and we can see the output now. It says blob, got a space, and then it says foo. And so
Or food.
Oh, yes, for food. Yes, for food. So what's going on here, right? Maybe let's see if maybe we're missing some data, right? Maybe there's some binary data that's not being displayed. Let's pipe this into hexdump and see what's going on. So if we take a look here, we can see we have blob space 4, and then we have a null byte here, and then we have FOO, and then here we have that last character is our new line that we had within the file. So basically this first part, the blob space 4, that is the object header. So in this case, this is our blob object, and it's written out in plain text. It says, okay, we have a blob space, and the 4, that is the byte size of everything that comes after the header. So in this case, we say we have foo plus the new line. That's 4 bytes. That makes sense. That's kind of our representation here of the uncompressed blob object.
So you did FOO and it put in the new line?
Yeah, whenever we did the echo and into that file, echo appends a new line by default unless you tell it not to. So that's kind of where we're at right now. So now let's go ahead and take a look at another one of these objects. So we'll take a look at this one here. Okay, what do we got here? We got tree. Okay, we probably assume that's part of our header there. We got some numbers there. We see foo. Okay, and we got a bunch of gibberish there at the end. Well, what the heck's going on there? Let's go ahead and also pipe this into hexdump. Maybe we can get something more useful out of that. So we can see here is once again we have our header terminated with a null byte again. So we see we have tree, which this is our representation of our tree object. And then we know it's going to be 31 bytes in size, and then there are null byte. Okay, we got that. So what's everything else in here? So we can see the 100644, that's the file mode for the tree entry that we have here. So if you're familiar with Unix permissions, right? In this case, so the first 3 there are Git specific. It's telling us about what that this is a regular file, and then we see 644 here saying what the permissions are of the file the tree entry represents. And then we can say this says foo. Well, okay, that's telling us that the tree entry that this is, the name of the file in the tree entry is foo, right? Which makes sense because our file was called foo. Then everything else out here, we see a bunch of gibberish after this null byte here. When we look really closely, yes. If we look really closely, we can see that in 25, 7C, C5, 64, that actually matches exactly the object name of the blob we were just looking at. And so what we can see here is the tree entry itself is pointing to, says, hey, I got a blob with this name, these permissions, and it's pointing to this object in the Git repository itself. So we can already kind of see kind of a link here of how trees are now pointing to blobs. If we had additional tree entries in here, there could be other types pointing to other objects. And so we kind of see how the beginnings of the tree is forming. All right. And lastly, let's go ahead and take a look at our commit object, which is what's left here, which is objects 9. Cool. And from here, we can see kind of the same thing here. We see the beginning commit space, and we see 173, which we can assume to be the byte size of the content here. And then we see some the actual content of the commit itself. So the first line here, we see that it says tree, and it has then a name of an object. And if we look closely, 205F 6B, well, that in fact refers to the tree we were just looking at. So we can see here we have a commit that's pointing to the root tree of the commit itself. Cool. Then we see some other information here, like who the author is. It's me, my email, committer information, and we of course see our commit message in here. Cool. So this kind of highlights exactly what the each of the objects and what they kind of look like here. All right. So next one we're going to do is let's go ahead and all right. Oh, okay. One thing we've actually neglected to talk about up to this point is where do these object names come from, right? So are they random? Are they not? If you've been following along, you'll see that some of them directly match what you have. And so it can't be completely random. Well, in fact, what's going on is Git's taking the uncompressed contents of these files with the header appended and basically taking a SHA-1 hash of that. And the output of that hash is the actual name of the object itself. And so this is referred to as a content addressable file system, meaning that the actual content itself is used to create the address that we use to acknowledge and grab each of these, reference these objects. So let's demonstrate this. So let's just pick one of the ones we previously just dumped into standard out. And let's go ahead and just pipe that into SHA-1 sum, right? If we do that, well, if we look at the output, we see that it actually matches the name of the object we have, which that makes sense. That's what we would expect. So cool. Now, this is actually a really important feature of Git, how this works. Because if you think about it, so what it means, because the actual value of the key here is derived from the value itself, this kind of has some cascading effects. So let's take, for example, let's say we have our file object, our blob, and we make a modification to it in some way. Well, we've updated the content of that blob now, which means when we go to take the SHA-1 hash of it, we'll get a completely different hash, which means that we need a new object now written into the database itself. And this has further cascading effects, because as we just noted, the tree itself references a blob. And so if I've updated the blob and it now has a new name, the tree needs to also be updated to point to that new blob name. And consequently, the content of the tree has changed, which means when we go and hash that tree, well, now it's also a new object that's going to have to be written. So let's go ahead and demonstrate this. That's a lot of words and a lot of things, so it might be easier just to go ahead and see this. So what I'm going to do is I'm going to make a modification to the repository. So what I'm going to do is I'm just going to append to our existing foo file just another line that says bar. And so if we now cat foo, it says foo bar. Cool. All right. And what I'm going to do is we're going to go ahead and add this. We can see that this change is staged now. And what I'm going to do is instead of creating a new commit on top, is I'm just going to rewrite the existing commit. I'm just going to amend it so that we just replace it basically with this new change. So I'm going to git commit -- amend, and I'm not going to edit the commit message or anything. So we're just going to leave it as is. And if we go run a git log, we'll see we still only have one commit. But if we look at the contents of our working tree, we can see we've made that change and it's now stored within our repository. Cool. All right. Let's now actually inspect, though, what's changed with our repository itself. So if we take a look at the objects directory, we can see that we still have those previous three files. Those three objects are still there. They remain unchanged, even though we've overwritten the commit. Those three objects are still there. And we see there's now three new objects, which that makes sense because we've modified the blob. So that means there has to be a new blob. Consequently, that meant the root tree was updated. So there's now a root tree. And of course, we modified the commit. So the commit's now pointing to a new root tree. Even though the commit message, the author, all that information is the same, now pointing to a different root tree, different hash, etc. So let's go ahead and just kind of view this. So what I'm going to do is I'm going to use another plumbing command here just to figure out really quickly what is the name of the new blob. So we're going to use a path scoped revision here, which I'm not going to go too much into. But this is going to tell me and print out what is the name of the blob object that we have now. And previously, I think it was 25 something. Now we see we have that new one there. And what we can do, and I'll introduce another git command that we haven't yet used, because it's kind of tedious to constantly go use pigz to decompress everything. There's actually a plumbing command called catfile. And catfile basically allows us, Git basically will automatically decompress that and return us the contents of the file. Kind of handles that all nice for us. So if I take git catfile -t and pass in that new blob name, we can see that it tells us the type of it. It's a blob. Cool. That's great. And then we can also push do cat file -p for pretty print, hash in the same hash, and it'll actually print us out the contents of that blob itself. Cool. And it automatically strips the header for us, so it just shows us directly what the contents are of that blob. And in fact, we can use this to go check out what the previous contents were of the last blob, which I believe started with 2.5, and we'll grab that right there. And we can see there's our old blob still there with its contents too. So neat. And of course, we can take a look at just grab what this is our new tree that we have, which we can see exists over there. We can also hit cat file. It will show us that, hey, that's indeed a tree object. And there's the contents of our tree. This is nice because it actually pre-prints this for us. We can see exactly the tree entry. We had multiple tree entries within this tree. There would be multiple lines here. You have a question?
So in the contents, why do we have the first couple of bytes as the directory in the objects directory? Why do we have 20 is the directory, and then that contains the file with the rest of the hash?
Yeah, that's a great question. So what Git does here is it basically fans out. So the actual object name is the concatenation of that two. These are all hexadecimal digits, right? So those 2 hex digits at the beginning are the directory name, and then the remaining, so the SHA-1 hash, there's 38 or 40 total hex digits, 20 bytes. And then the remaining 38 are the file name itself. But the actual object name is the concatenation of both. And the reason Git splits these out across is really just an optimization. There can be many objects within the Git repository, in the objects directory itself. And you can run into problems if you have too many files just in a single directory. And by basically taking the first 2 hex digits, which is 1 byte, so that's 256 potential options, it's able to fan out all the potential objects across 256 directories at most. And so it's just an optimization just to help avoid things like inode exhaustion and other concerns like that. That makes sense? Yeah. Okay, cool. All right, so let's see where.
And there's other blob that is still there because they have a garbage collector.
Yes, yeah. Are you talking about
The old one.
the old one? Yes. So it is technically unreferenced. So that's a good kind of segue into the next topic here. So something we've noticed is that we still have those 3 old objects that exist, even though there's nothing actually referencing them directly, but they still exist. This is actually a really kind of cool and powerful, convenient feature of Git, because whenever we're making modifications to our repository, we're computing the hash on its contents, and we're adding new objects to the repository. We're not taking away things, at least immediately. Everything's there, it's still there. Like, we were able to go inspect the old blob, we could inspect the old commit even if we wanted, right? All of it's still there. And Git actually, so if you know what to look for, if you've rewritten history in some way and made a mistake, you can actually go easily recover and get back to that previous state because all the data is still there. And Git actually provides a very convenient mechanism to do this called reflog. And as alluded to earlier, so if we train here about Git directory, we have this logs directory here. And this is how Git kind of tracks, it logs kind of the history every time we make modifications to a reference itself. And what we can do is we can use the command git reflog, and we can specify the branch, the tip we want to see the history of, and it'll kind of tell us what's happened, right? And so we can see here at the bottom, we see, hey, that was our initial commit we made. And then we see above that, that's when we amended that commit. And so in fact, if we want to go back to that previous state, we can really easily. In fact, what we can do is we can copy the short SHA here of the original commit, and we can just say git reset --harp, put that in, and now we've reset. We actually go type in git log now. Well, that doesn't really tell us anything. But if we cat our our foo file in our index, in our working tree, we can see we've gone back to foo. It's no longer foo bar, right? So we've been able to successfully reset ourselves back to the previous state, because Git kind of keeps track of all of that data, which is very, very useful. Yes?
Is that a detached head?
No. So detached head, let's see, that's the best way to demonstrate that. So I'll demonstrate, because that's actually a good question. A lot of people get confused at what a detached head is.
It's a scary thing to encounter.
Yeah, and some people can get it. It's actually really not that bad. And in some ways, it's a very useful tool as well. So all a detached head state basically means, if you've ever found yourself in that situation, is basically when the head file doesn't point to a reference directly. So the head file itself is what we call symbolic reference. You can kind of think of it as like a symlink or a shortcut. It doesn't actually reference something typically directly. Instead, it points to something symbolically, right? And so, but you can, sometimes you can actually, in Git, you can check out whatever you want. You can check out some branch, but you can also check out a commit directly. And that's where you can end up in like a detached head state.
So like right now, if you were to check out the thing that you just completed, you would be in detached head.
Exactly. So we'll do that right now. We'll do git switch. We'll put -d because we want to force it to go into a detached head state. And we can specify the commit here. And now you'll see it no longer says I'm on master. I'm now in 9E57, which is actually the same commit the master points to, but I'm directly checked out the commit. And if we actually tap the contents of head file, we'll see that we are actually, it doesn't no longer says, refs heads master. We're directly checked out that commit on there. And this kind of puts you in like a read-only state to a degree. I mean, not really. You can technically add commits and everything towards that on top of that, but you're not modifying really any references. Like when you're in this state, if you're committing and making changes, you're not updating the reference that you currently checked out.
So if we want to go back to a specific commit, git reset --hard and then the shard. That's
Yeah. So
proper way of doing it.
Yeah, so git reset is more of a way to take where you're currently at, like the reference you're at, and you're going to reset to a specific known state. So I'm going to say, because if we go back to where we were,
I mean, it modifies your file system a bit. Not just
yes, correct. Yeah, it'll modify the working tree to match that exact state. Correct. So we go back to where we were previously. I think
what I was going to suggest is if you check out the AE one, then that's how people like probably normally get into a detached head state. If you say check out the AE 59 whatever.
Okay. Yeah. That's just another commit, I believe. So let's do that one. And
What? I mean, if you do a checkout, it's how people are probably normally going to get.
oh yeah, okay. Yeah, most people will still use checkout. Switch is the new hip way of doing things. So that's fine.
Right.
Yeah, we can check out AE. Let's see. Oh, that one's not a commit. Let's see. What was one of our commits? We can just get ref log, math, spell it right. It was, and just real quick aside, you can see that when we did reset, it also appended another entry to our ref log that we can see here. So that we reset to something. So even if we reset to something, we can go back to it, right? As well. So if we want to go specifically, well,
You want the 60 year.
yeah, let's do that one. Yeah. So what we'll do is we'll check out this guy here, and basically our reference for master remains the same. So if we actually want to take a look at what master is pointing to, we could cat .git /refs heads master, right? We'll see that master is still pointing to 9E57, but currently I'm checked out to 606C8. So that kind of makes sense?
Yeah.
Okay.
It does.
Cool. So now we're back to where we were before. All right. Let's see. Where were we? Okay. So kind of the last thing we've really neglected to talk about up to this point is we've kind of showcased all of the different objects within Git and how they all link together and are kind of structured. But we actually haven't had an example with multiple commits yet, which is kind of the most important part about Git is that you can provide additional commits. So how can we actually to provide what our actual versioning? So let's kind of showcase what that looks like. And it's actually, now that we kind of have some of the foundations, fairly simple. So we're going to go ahead and make another change to our repository. I'll do something simple. We're just going to rename foo, the foo file that we have. We'll just rename it to bar. We'll cap the contents of that. So,
It's bar.
oh yeah, sorry, it's bar. Just did that. And we can see that it says foo there. Cool. So we've renamed it. We'll go ahead and add it. You can see that the change of stage gets detected as rename. And we'll go ahead and this time we'll go ahead and create a new commit. Let's call it rename. Correctly. Rename. And if we take a look at git log here, we can see now that yes, we do indeed have 2 commits now. Cool. So let's see how this commit exactly refers to the previous commit. Because something to note here, when we're running git log, what it's really doing is we're running git log on whatever reference we have checked out, and Git's just walking backwards through history and just figuring out what are all the commits that it needs to see. So let's use our friend cat file again. Actually, just grab whatever references for it. It's that one, and we're going to commit cat file -p this commit. And what we'll see here is we see indeed that it has that first line still, which is that tree entry pointing to the root tree that this commit is a snapshot of. And then we see another line here that says parent. And this parent points to 9057. And this is the kind of ancestor of that commit. It's its parent. So if we actually take a look at this guy, copy him, git cat file -p. There's our first commit. So we can see Git is able to maintain in its commits kind of point down the line of everything. Something to keep a note though is this. So in this example, we have a linear history where our commit only has 1 parent. You can have things like merge commits where you can actually have 2 or even more commits. If you have more than 2, and we call those octopus merges. We don't see those very often. But with merge commits, a single commit can actually have multiple parents. And an easy way of seeing that, I'll just look at it. I'm just going to look at a repository that has a bunch of commits already in it. You ever seen like a commit graph before that looks something crazy like this? We actually look at the top commit here, the very, very top. We can see that it has a pointer pointing to 2 different commits. One that's right over the right, one that goes all the way down there to that guy right there. So that's really indicating is that top level commit, which is the most recent one, has 2 parents, right? And during this merge commit, we just kind of merge together history into a singular snapshot of what's going on. And so, quick, and we can demonstrate that in this repository also by just doing git cat file. And we'll see if we look at the contents of this commit that indeed has 2 parents. And that just makes it a little bit more special. So, cool. All right, so really the last thing I wanted to talk about here, just to kind of clear up some things. So if you've ever worked in a repository, and let's say you clone a repository, and you want to go peek into the .git directory itself. So I have a repository here, just the Linux kernel that's good to show. Something you may know, so the Linux kernel, massive project, has millions and millions of objects in it. But if we take a look at its objects directory, this is a clone I did of it, we'll see there's no objects. What the heck? This should have millions and millions of objects. That's because Git actually, what it does periodically is actually packs all of those objects into what it calls a pack file. And we can see a whole bunch of those there, these pack files prefixed with pack. And it does this to kind of optimize, because if you have millions and millions of objects, even if you're fanning them out across, all of those directories, you're going to run into problems like inode exhaustion or something. So it's best that, and we can actually even save more space by doing things like delta compression and other things to really reduce disk space. And so we Git will periodically compact everything into these pack files, usually when it does things like garbage collection. So, all right. And we can kind of demonstrate that in our own repository. If we just run git gc, this is a porcelain command that will actually spin off another process called git repack, which will actually pack all of our loose objects into a pack file. When we run that, if we tree our Git directory, we can now see all our loose objects are gone, and they're now packed into that pack file. Cool. So that's pretty much everything I want to cover. So hopefully this is somewhat informative and give you a better aspect into look into how Git works kind of under the hood. And if anyone has any questions, I'm more than willing to answer them. And if not, that's totally cool too.
So does GitLab reuse all the normal Git packing, or do you have your own special sauce?
No, we actually build directly off of Git. In fact, Gitly, it just spawns Git processes. Anytime we need to interact with the repository, almost always, sans a couple of things we'll re-implement ourselves. We work directly with the object data model of Git. And so on the back end, it's just Git repositories, exactly normal Git repositories. And we're forking, execing, spawning a whole bunch of various Git commands to do various tasks. So we'll do like things like housekeeping. Whenever you open like a merge request, for example, and you view those diffs, on the server side, we're spawning Git diff and rendering all of those diffs and passing them forward to the client. Yes.
What's the weirdest Git command that you used?
Weirdest Git command. I don't know. I don't know if I use anything super exotic on a day-to-day basis. I know what I'll say. I Git send email. So because I work up on the mailing list, and this is technically an external Git command. It's not, I think, a main part of the project. But when you work on the mailing list for Git, they do things very old school. They have a mailing list. They don't host. There is a mirror of the Git project itself that's hosted on GitHub. There's also one on GitLab and some various other Git forges. We work with sending patches directly by email, and so you can use Git send email to take patches that you have, send those up to the mailing list and whatnot.
You know, you can write your own Git command very easily.
Very easily, actually.
Wow.
All you do is you put Git batch whatever in a directory that you can path. You would Git command.
Yeah, actually, I think I have one here. I wrote so Git's super extensible. Like you mentioned, if you have any executable that's prefixed with Git dash, and that's within your path, if you, I not have any more. I don't remember. I had something funny at one point, and if you execute, it'll just basically Git will execute that. It'll look for that executable that matches the pattern, and will spawn and execute that.
So does Git use the SHA to check integrity on the blobs and the Git objects later? So if you were to like go in after the fact, after the SHA was calculated, and like change the contents of one of the objects, would Git be able to detect that later on?
So I do not. I can't remember off the top of my head. I don't actually think it validates the consistency of the content itself. I'm pretty sure it doesn't. I can't remember off the top of my head. I'll have to look into that.
I think there are commands too. I don't know.
So there is a command git fstk, and what that command does is it validates that the connectivity of the repository itself. So something to keep in mind, and this is kind of generally why people don't go and peek into the .git directory and mess with stuff, because if you mess with those files there, you can very easily corrupt the repository. If one object is missing in the middle of the chain, the repository becomes corrupted, because in order for you to have a complete repository, it needs to be able to connect through all of those nodes within the tree. And so if anything's missing, you have problems. So there are commands like git fstk, which will actually go and validate, performs what Git calls the connectivity check to ensure that everything is there and present in the repository. But I don't think it actually validates the hashes themselves.
So the objects stores all of the objects on all of the branches for the whole history of the repository.
Mm-hmm. Yes.
And then when you're pushing changes to other repositories or pulling changes down, then those commits are objects that are added to your tree.
Correct, exactly. So kind of a fun little thing to think about is whenever let's say you're fetching changes from a remote repository, what's going on basically is when you call fetch, it reaches out to the remote, It spawns another it's Git upload pack. Yeah, it spawns Git upload pack on the remote side. And what this does is it essentially it first performs reference negotiation, and so it looks at all of the references you have, because if Git always assumes that your repository on both ends is not corrupt. It makes that assumption that they're not corrupt. And what it does is says, okay, you have all of these references with all these tips pointing to here. And I have all of these references pointing to these tips here. And it's able to basically compute the delta between those and say, okay, if I have all these references and you're missing some of these, okay, in order to fill you in, I need to send you all of these objects, right? And it's able to walk down to the graph to the last known part in the graph that you have. And then it packages all those objects up into a pack file and then sends that pack file over the wire to use the client.
It's true that when you're receiving objects for a wire, everything is checked for integrity. Otherwise, it'd be way too easy to do that for malicious actors.
Yeah, it might. I just don't know off the top of my head.
I think it's checked on a regular basis. Because malicious actors.
Yeah, that would be definitely a concern.
But so Git is designed to be a perfectly complete version control system without any type of remote involved.
Exactly, and that's kind of the distributed nature of it. If you're familiar with CAP theorem, right? It emphasizes availability and partition tolerance to its fullest. So there's no guaranteed consistency across one Git repository to another. In fact, there really isn't the idea of like the centralized remote that we keep on GitHub or GitLab. That isn't really innate to Git itself.
It's a convention.
Yeah, it's just convention, exactly. When you have a copy of your repository, generally speaking, there are asterisks here. You have a complete copy of the repository itself. Sans you doing some very more advanced stuff like shallow clones and partial checkouts.
Awesome. Well, thanks, Justin.
Yeah, thank you.
Super cool.
Okay.
Super excited. Where can people find you if they have more questions or they just want to bug you about your job?
Oh, yes. You can easily just find me on LinkedIn, I guess, and message me there, or also on GitLab. If you have a GitLab account, Justin Tobler, you can bother me there. So,
So if you want to see
reason
them, you can
to
see what he does for work.
yeah.
So what's the biggest reason you use GitLab over GitHub?
I think the biggest reason for GitLab, I'm a little biased, of course,
Sure,
obviously, being I work there, is it's really the complete platform. There isn't, with GitHub, you have to have a lot of other partial solutions still tied into the workflow, but GitLab does a pretty good job of providing kind of the full suite of everything, from just repository storage to CI/CD to security scanning, all of that. It's kind of just baked into one platform.
Well, I'll tell you my reasons. So one, you guys have a self-hosting alternative.
Oh yeah, that's a big one too.
That's a good one. And then another one is you call them merge requests, not pull requests.
The names.
That's such a better name. Pull request.
So I haven't used GitLab in a couple of years, but when I used it, and this speaks to your, you need, you have everything in one complete thing. That model didn't work with how I needed to work. And so for the equivalent of like GitHub pages, it's like I had to run a CI/CD, and I'm like, that's way too complicated.
Yeah.
I mean, for me, it's like I have other things to do than to write, scripts to just publish the internal stuff. And so I don't know if it's still like that, but that was.
I'm not 100% sure. I know these days, though, there's quite a few templates that just basically come pre-baked to do a lot of the various the standard CI operations. So you don't have to do very much to get it up and going.
Right.
So I'm not 100% sure on that.
But it seemed like the whole tool was like CI/CD is our main hammer, and everything else kind of fell.
Yeah, it's definitely kind of
That's how it felt.
the big thing. CI/CD was a big component. It's still a big component.
The both.
Yeah, but like you said, in GitHub, it was you could pick and choose. You didn't necessarily need to. You could just use it for just to get for serving pages and stuff like that without that.
both very versatile. One's more popular and one's more popular with,
Yeah, one's
companies.
basically the de facto standard for open source, being that GitHub, and the other one's
Mhm.
basically the de facto standard for enterprises.
So super cool. Really appreciate you for coming out, Justin. So one more round of applause. Thanks for coming, everybody. This was, I think, our fourth or third installment of our general meetings, and super excited to have y'all here. Big shout out to Project Cowork, actually, the building that we're in, and our further partner, Tech Block from San Antonio. So make sure you check them out. If you haven't already, or if you're looking for a project or a co-working space, definitely check them out and leave a review if you liked it here today. Outside of that, we have more stuff coming up in the next couple weeks. We actually have our ACM series talk, actually presented by Gene over here. He's talking about React Native. He's going to have a second video tomorrow. That'll all be virtual. Next week, we'll actually be here again on Thursday to present his final video. So definitely check that out. Geeks and Drinks monthly meetup is happening on September 4th. Okay.
I just wanted to mention that the React Native stuff is being recorded on YouTube, right?
Yep.
So you can go catch up on previous ones if you miss it.
Yeah, so if you missed that time, no fret. It'll be recorded similar to how this meeting just was, excusing the hiccup in the beginning, so I was figuring everything out. But yeah, so definitely check out the upcoming stuff. I know I mentioned this group on here. They're pretty cool. They're pretty recently starting up again. They're just like, if you like lock picking, kind of like the vibes.
Lock picking?
Yeah, if you like
Wow.
picking locks. So it's a group about that. So again, if you don't follow us on social media or follow us on Meetup or our Luma calendar, or you're not on the DevSA Discord, definitely check those out. We'll have those links posted and stuff. I'll leave them up for a second. But again, thank y'all for coming out. If y'all have any more questions or questions for myself or my team back there, definitely let us know. If you also want to speak at some event like this, we have availability coming up in the next few months. So if you have a topic you're pretty passionate about, reach out to us. But other than that, thanks for coming, y'all. And thank you again, Justin.
Yes. And take pizza with you, or
Yeah, take some
stay
pizza.
here and eat lots of pizza. One thing that, so